So in this question, we can see that what we have in our square root is in the form of a squared minus x squared. And whenever we have something in this form, we use our substitution of x is equal to a sine u. Because our a squared is 4, that means our a will be 2. And therefore, for this integration, we are going to use trigonometric substitution, and we are going to make our x 2 sine u. Therefore, our dx by du is going to be 2 cosine u, and we can therefore write our dx as 2 cosine u du. We now have something that we can substitute in place of x as well as in place of our dx. We can therefore rewrite this integral now as the integral of 4 minus 2 sine u squared root 2 cosine u du. We can expand the brackets and rewrite this as 4 minus 4 sine squared u, and we've still got 2 cosine u du. We will now factorize the part that is in our root, and we can rewrite it as 4 bracket 1 minus sine squared u 2 cosine u du. Using our trigonometric identities, we know that cosine squared theta is the same as 1 minus sine squared theta. We can therefore substitute our 1 minus sine squared u with cosine squared u and rewrite this as the integral of the root of 4 cosine squared u, and we've still got the 2 cosine u du. We can work out the root by separately finding the square root of 4 and the square root of cosine squared u, and we can rewrite this now as the integral of 2 cosine u, and we've still got the 2 cosine u du. We can now multiply the 2's together to give us 4, and we can put the 4 outside our integration sign, and cosine u multiplied by cosine u is cosine squared u du. Using our double angle formula, we know that the cosine of 2 theta can also be written as 2 cosine squared theta minus 1. In our integral, we've got cosine squared u, and using this identity, we can try and make cosine squared theta the subject. So if we add 1 and divide by 2, cosine squared theta is equal to cosine 2 theta plus 1 over 2. We can therefore now rewrite our integral with 4 on the outside of our integral, and instead of cosine squared u, we can now write cosine 2u plus 1 over 2 du. If we just simplify that now, we can now write this as 2 on the outside and cosine 2u plus 1 du. We can now easily integrate this, so our 2 remains outside, and the integral of cosine 2u can be written as sine 2u over 2, and our 1 integrated becomes u. We can expand the bracket and write this as sine 2u plus 2u plus c. Using the first part where we wrote x is equal to 2 sine u, we can make u the subject and write our u as sine inverse of x over 2. In our equation so far, we have sine 2u, and we know that this is a double angle formula for the sine of 2u. We can rewrite that as 2 sine u cosine u plus 2u plus c. Now all we need to do is rewrite this in terms of x again. So we already have our substitution for 2 sine u, which is x. We already have a substitution back for our u, which is sine inverse of x over 2. But for cosine u, using our x is equal to 2 sine u, we can derive a value for sine u, which will be x over 2, meaning that if we drew a right-angled triangle with an angle u, the opposite side of this triangle would be x, and the hypotenuse would be 2, giving us an adjacent of the root of 4 minus x squared. Using this, we can now derive a value for cosine u, which will be the root of 4 minus x squared over 2. We can therefore replace our u's now with the original x's. So for 2 sine u, we can write that as x. For cosine u, we can put the root of 4 minus x squared over 2. And for u, we can put the sine inverse of x over 2 plus c. So instead of writing it in this way, we could also write it in a different way, where we replace the sine inverse with arcsine. So we could write exactly the same thing, but instead of the 2 sine inverse x over 2, we could now write that as 2 arcsine x over 2. And this is our final answer for the integral of the root of 4 minus x squared using trigonometric substitution.